And now we're going to hear from Jordi talking about verifying SNARKs with SNARKs. Yeah. He's just getting you set up there. There we go.
Perfect. Thank you, Anna. Okay. Hello, everybody. Sorry for my voice. The week is long. I'm Jordi Baylina. I'm the technical lead at Polygon Hermez. What I want to explain now is I'm going to zoom in one of specific piece that we are using in Polygon Hermez is verifying a SNARK with a SNARK. So just to mark where we are is mainly if we see the prover, what we want to do mainly is taking a set of transactions, Ethereum transactions. We are code compatible, so this is our Ethereum transactions. We are getting a state root, and when we are proving that we have a new state root. For this, we generate a bunch of polynomials. That's all those polynomials need to fulfill specific identities. Bunch of identities. The prover, for example, we have around 1,000 polynomials, maybe a little less, but around that number, order of magnitudes, and and constraints maybe twice as that. It's just a lot of constraints and a lot of polynomials. And we have a synthetizer, executor if you want, that actually takes these transactions and generates I don't know if this works. Oh yeah, good. It generates these proofs. So these polynomials, this array of polynomials that fulfill this proof. Okay, what do we do with this? Well, the first thing we do is we generate a proof, and we generate a SNARK proof. Actually, we are working with small field elements. So the SNARK proof generation is it's quite fast to generate. We are using a small blow up, so we don't care. As we will see, because we have other things later, we don't care about the size of the SNARK, because later we want to, at the end it's going to be a SNARK. So what we care is in the full proof generation, so that you don't have many constraints later on, and so on. So once we have this proof, that may be big, but it's just a proof that has been computed quite fast, then we can have this, optionally we can have this tree of proof, so we can aggregate many transactions or many blocks of transactions in a single proof. And finally, in the last step, once we aggregate all this proof, maybe with a kind of a tree, then in the last element, we have a prover that prove this SNARK proof, and generates a SNARK proof. This SNARK can be Plonk or Growth 16. At the end, it's a normal R1CS circuit or Plonk circuit, just standard Plonk. Here we are not even talking. Well, we will talk a little bit about possibilities there. Okay? And what I'm going to focus in my presentation is mainly in this part of here. So it's how we generate this Growth 16 proof that we generate this. So in order to understand that is, okay, what means verifying? What means verifying a SNARK? What are the computations, what needs to do? Because all these computations are the things that we need to put in a circuit. Actually, we're using Circum. Circum is going to be a circuit that you have as an input, private input. It's going to be the proof, the SNARK, that comes from the low side. Of course, it also will have the public input that hashes all the public inputs. It's just single. We are working with a single public input. It's going to come here, and this is going to be like part of the verifier of the SNARK. So it's going to be one piece in there. So if we just zoom in here, what pieces? What we have to do here? Well, the first, this is very common in these polynomial commitments. We have a transcript, and we need to compute about this transcript. We need to compute this randomness through this transcript. This is quite easy, but at the end, what we need to do is mainly hashing. That's the main operations that we need to do here. Okay. The second part is actually checking those identities. We have a lot of polynomials. We have probably an evaluation of those polynomials at some specific point or points, and then we check at that specific point, and if the random number is okay, then that means for some math theory that, for probability, that this is going to be okay. This is a little bit more tricky when you are working with small field elements, because you need to work with some extensions, but the idea is exactly the same. So here we see that we have a lot of operations on that. Next step is we need to do queries. Actually, a Stark mainly is it's a Merkle tree of some Merkelization of some evaluations. So we need to do queries, and queries are mainly hashes here. Okay. The other thing we need to do is calculate. Well, we need to verify that these evaluations are right. So we need to calculate the opening polynomials. Okay. We need to do that for each query. So if we have a lot of queries, we will have to do these evaluations of the opening polynomial many times. And then we have the fry. The fry we have when we go upwards and downwards, we have different queries also to the Merkle tree. So we have here a lot of hashing, and we have also we need to do this. We need to check. So the idea is that we need to do evaluations. So the idea is we have a polynomial of degree n, or degree less than n. We have n points, and then we need to evaluate that a specific point and check that this match with the downside polynomial. And we need to do that in each, so recursively until the polynomial is going with a low degree until we are at the end. And at the end, the remaining polynomial, we need to do maybe some check there. So this is a structure of a verifier, more or less, and we have to put that in a circuit. Okay, so how we do that in a way that's cheap, that means with small constraints. Here, the difference, so in general, the people that's designing Starks, they try to reduce the size of the proof. Here, what we are trying to do is trying to reduce, actually, is the number of constraints for the verifier side, but also the proof generation. So everything, at the end, what we are trying to minimize is the full process of the final proof computation time. Okay? So what's the naive way? Well, the easiest way is if we just generate the Stark with the same field. We want to use BN 128 because this is the one that's easy to write, growth 16s or Plonk in Ethereum right now. I hope that at some point BLS 1381 it's available. But this is what we have right now, so it's at 256 bits. So we can work with these polynomials, generate all the state machines with these 256-bit fields. But then this is expensive from the generation of the proof, but it's more cheap in it's straightforward. For the hash functions, you can also use some Plonk, some circuits, some ZK hash functions like Polygon, in order to save constraints in the circuit. But what happens if we have a mix? In this case, we have a mix of prime fields. So we have there are parts of this. For example, the hash functions, we can still use Poseidon, and we can still use these friendly, circuit-friendly or growth 16-friendly functions to build the Stark. So this does not change. But for the specific, when we need to do, for example, we need to check the operations in the polynomials, we need to work with this small prime field here. So how we do these cross-prime multiplications? What's the cost of doing a cross-prime multiplications inside the circuit? Well, actually, what mainly you do is, well, we imagine that we want to do a multiplication. So A times B mod PP is 64 bits number must be equals to R. Okay, we can put exactly the same equation, but in mod Q. So A times B, here it can be some multiple of the prime number minus C. This must be equal to 0. This equation is okay, but might be overflow because we are in a prime field. So what we add is we add two range checks. mainly. So if we guarantee that C is less than 2 to the 64 and R is less than 2 to the 64, we guarantee, well, then we are done. We may have two solutions, but we know that these solutions are small enough, are only 64 bits, and this is enough for what we need. Okay, and this is a total. Each range check is, if it's 64 bits, is more or less is 64 constraints. Here, if you have carries, maybe it's a little bit more, maybe it's 129 or 130 for the carries altogether. We are working. Sorry, we are working with extension fields. So actually, well, when you do an extension field, you do maybe 6. If you are doing an extension field, for example, of 2, is maybe you need to do 4 multiplications. If you're in extension 3 or an extension field of 3, maybe you need to do 6, 9, 6, 7 multiplications, depending. But it's out of the stage. So. You need to do these different multiplications, but you can actually do a trick, and actually you can put this equation a little bit more longer, and you only need, at the end, you don't need that many. You can pack them together. So at the end, you just need like 3 times. If it's an extension 3, for example, you just need 3 times this range check. So for doing an extension field of a 64 bits, we just need less than 400 constraints. Okay, so let's do some numbers here. Okay, is it possible to build that? Well, let's start with the first example. Imagine that what we want to do is, well, for hash functions, normal hash. If we are doing hash of, if we are doing trees of 16 elements per slot, then the hash of actually is T17. So 16 inputs, and you just hash with a single hash. This is, in Poseidon, is 612 constraints, which is very low compared to, say, SHA-256, which could be like 30,000 or something, or around that. So it's a good hash on that. And yeah, so if we have a query, then a query of 2 to the 24, so this is our 6 steps, so this is going to be 300. So let's start with simple example, is what happens if we want to validate this, just strike forward. So we want to take directly one of those proof systems, so one of the that are proving EVM transactions, and we just want to prove that directly, just directly to the Ethereum. So we just want to generate this gross 16 out of this. Well, in this case, we have around 1,000 polynomials. We have a blow-up factor of 2. That means that we have to do a lot of queries. In this case, 128 queries. The polynomial size after blow-up, we take 2 to the 24. This is just some example numbers so that you see where we are. Just take it as just as a reference, as a rough numbers of where we are. Okay. So number of constraints. Well, if we have 100 polynomials, maybe it's 2,000 polynomials. Let's put 2 multiplications per constraint, just as a rough number. Okay, so we have a total for, well, this is what we have. So what would be the numbers? Okay, was when then we need to go like step by step and check what are the numbers here. Okay, the first step, which is the transcript, this is quite constant and it's just some hashes, which is quite low, and this is could be, I put it, it's going to be below 5K, just rough numbers. This depends very much on the circuit. If you have many interactions, you need more primes, and can depend. But in this case, it's quite low and quite insignificant in the full system. Checking the polynomial constraints, here in this case, we have a lot of these cross-prime fields. This is, when you see a 390, where it is? The 390 here, this is the cost of the multiplications. So we have 2,000 constraints times 2. This is at the end is 1.6 constraints. Okay. You see here that we are using diffry, so we are only checking once this. So we have single opening in the full system, so we only need to check once. This is one of the advantages of using diffry here. So the next step, and this is, you see an end here. So this, in this case, we need to do this for each query. The next step is we need to check the evaluation. We need to check that the evaluations, the openings, are correct. Okay, and we need to evaluate this opening protocol there. So in this case, this is, well, it's quite important, mainly because we have with this 128 here. So this is about 5.3 million constraints, which is quite a lot. If we go to the different steps, calculate the opening polynomials, this is the, we need to do this. This is the opening of all the points, of the evaluation points. So this is the 612. This is the hash cost. So this is in total 5.3 megahertz, and the evaluation of the polynomials is 0.8 megahertz. Is 390. Okay. So in this part, here is what we need to do every time. So this is the fry part. In the fry part, this is the 6, 5, 4, 3, 2, 1. This is because we are in each one we are reducing 16. We divide by 16, so we are reducing 4 bits each time. So this is what we need to do that 4 times. This is this gives us 2.1 million constraints. These are hash functions. These end queries are also hash functions for the upper polynomial, the bottom polynomial on that side. Here we have an extra cost because here if we need 16 points, we need to hash these 16 points all together. And at the end, here is the part that we need to do this cross prime field. That's quite costly. It's 6 million constraints. As you can see, these parts are important because these are the ones that are cross-field, and that one makes all together. And in the last one, of course, the last polynomial, if you go quite low, this is insignificant. Maybe it's 1 constraint or something like that, or very few constraints. So in total, this is about 17 million constraints, which is an important circuit. Actually, with rapid SNARK, this circuit, it can take about 25 seconds in a 64 cores machine to generate. So it's doable, but it's a little bit costly. This is in gross 16. If we go to Plonk, then of course we can do these range checks in a custom gate. This lows a little bit. This can be lows. It can lower a little bit the number of constraints, but then the verifier in Plonk, it's a little bit more expensive because you need to do some extra things in the verifier. And the Plonk by itself is a little bit more expensive than gross 16. I know that the Aztec people is improving it and getting very close to gross 16, but in Plonk is a little bit more expensive. And the other thing is that because the structure of Plonk, well, the gates, you cannot do some optimizations that you can do in R1CS systems, so you have more gates, so you have an extra cost of the more gates here, and also you have some limitations because you need to in the Plonk you need to increase the degree like 4 times. So here we are very much in the limit of the curve. Here with 7.4, so that yeah. So if we are, I just get lost. Well, so yeah, we were talking about Plonk. So because you need to work with 4 times the degree of the polynomial. This gets worse in the curve, and we are reaching the limit of the curve. Here this would be in the 32 million constraints, the next power of 2. If we multiply by that 4, this is 128 million constraints, which is 2 to the 27, and the limit is 2 to the 28. That's a question there. Let's just, I don't know. I'm finishing. Let me finish the other, and then we do questions. Yeah. Okay. So just to finish, I will put another example. It's like what happened if instead of verifying this proof system, we just verify this recursive star system. So if we go back to the schema, we verify this circuit. This circuit is already a circuit that's verifying a Stark. This is much simple than verifying a ZK7. So you have much less polynomials. And here I put, let's see here. So just instead of 1,000 polynomials, I just put 100 polynomials. Instead of, well, we have a blow-up factor. Instead of 2, I put 2 to the 4. So we can only do, in this case, we only need to do 16 queries. We can do it on that. And just here. We keep the same size of the polynomial because there is a flow factor. Actually, is 1 million steps. So this should be more than enough to do to verify a Stark. And number of constraints, we keep exactly the same rule that before. Maybe 2 times the number of polynomials and multiplications times 2. If we do exactly the same numbers and we do the computations, then what we have is a circuit that's below 2 million constraints, and this is a circuit that can be generated, this proof can be generated in less than 2 seconds in a 64 cores machine. So said in other words, is that this last part of this verifying a Stark in a SNARK, if you compare to the total cost of generating the proof, this is, I'm not going to say that's insignificant, but at least is really, really low, and it's not the bottleneck in the prover. And now, yes, we can do the questions.
All right. Well, thank you for the talk. Maybe we'd give a hand. All right. So there was a question right here. All right.
Thank you for a great talk, Jordi. The question is, you say the Plonk is not particularly convenient because you have more constraints, but did you actually consider using custom gates for Plonk? Because if all of the constraints you're doing are just hashing like all the way and you don't need the generic.
Definitely. You know, actually, all these, you can have custom constraints for the hash functions, for sure, and you can have also custom constraints for the rank checks. The rank you can reduce instead. If you do this multiplication, why it doesn't work? It stopped working? Stop working this? Well, if you saw the multiplication, for each multiplication you had 64, for each rank check you had 128 constraints. In the extension was 390 constraints. You can convert these 390 constraints with a single custom gate block up rank check on all that. So in this you can reduce a lot the number of constraints. We need to do the numbers and we need to see if this worth. The problem is that the big limitation is not in the proving, it's not in the proving, it's more in the verifying. The verifying cost of Plonk is slightly more than Groth16. But of course, Plonk has a lot of advantages. For example, you don't have trusted setup, which is a pain to run. So I'm just taking this as Groth16, which is very straightforward, and you don't need to do like any things. And of course, there is margin for improvement. What I wanted to explain is a little bit what are the pieces in there, and just show that this is something that's definitively possible and it's not expensive in the context of verifying ZK7.
Jordi, I think your slides are working now, by the way. There is something on there. Yeah.
Yeah. And this this part here, okay? But also in the Plonk you can put this, you can put parts of the Plonk in. But the problem is that these custom gates, if they have if they increment the degree of the polynomial, you're also limited by the curve. In the BN you can only go to the 2 to the 28, and we are, especially in the first circuit, we are very much in the limit. If you multiply that by 8, we go above the 2 to the 28. Of course, you reduce in one side, but then you increase because you don't have multiplications. So we need to check, but it's not clear. So you need to do the work. What's definitively possible is in the second circuit. In the recursive part, this can be for sure done in Plonk, and this is probably how we are going to work on that direction.
You mentioned that one of the big motivations for using Plonk is that you can do these custom gates. If we could do a similar thing in Grot16, would that be useful, or would it be your long-term goal to move to something like Plonk because of the universal setup anyway?
I think it would be at this point, very interesting. But my feeling is that Plonk, in the short run, everything is going to run in Plonk, mainly because running a trusted setup for a specific circuit is a pain for most applications. So yes, it's useful, but I have doubt that in the practical, so that the practical people that's doing a SNARK application is going to use Grot16, because running a trusted setup, I run once, and I don't want to run much more.
I think we don't have time. I think, unfortunately, we don't have more time for questions, but you're sticking around, right? Folks can talk to you?
I'm around.
Okay, very good. Thanks so much,
Perfect.
Jordi.
Thank you, Anna.